This video provides key considerations to properly size a refrigerated dryer to optimize maximum performance and efficiency of your compressed air system. The primary purpose of having dry air in a compressed air system is to prevent corrosion, equipment damage, and performance issues caused by liquid water contaminating the distribution system. Atmospheric air contains water vapor, and the compression process, much like squeezing a wet sponge, concentrates the moisture present in the ambient air. If the pressure and temperature conditions within the piping system are favorable for condensation, liquid water will form throughout the compressed air system's distribution network. To protect products and pneumatic equipment from moisture contamination, the air system needs a compressed air dryer that uses one of the following air drying technologies: refrigerated, desiccant, deliquescent, or membrane. Of all these types, refrigerated air dryers are the most widely used. They're simple and reliable, but need to be properly sized for the application and installation environment to ensure a continuous supply of dry air. Experience shows that a significant portion of refrigerated compressed air dryers are improperly sized for their application, resulting in countless compressed air systems being contaminated with water. An undersized dryer will result in liquid water contamination throughout a compressed air system, along with an energy-robbing pressure drop. At the same time, selecting too large of a dryer increases capital investment and in extreme cases has negative results. A properly sized and operating refrigerated air dryer will supply dry air, void of any liquid water, for any industrial application that requires a 35 degrees Fahrenheit to 45 degrees Fahrenheit pressure dew point. Pressure dew point is the temperature at which the air in a compressed air system is 100% saturated with water vapor. When compressed air is exposed to a temperature below its dew point, the water vapor condenses into liquid water within the pressurized distribution system. The function of the refrigerated air dryer is to reduce the pressure dew point of the compressed air by reducing the concentration of water vapor in the compressed air. The dryer achieves this by cooling the air with a refrigeration system, condensing water vapor into liquid water, similar to what happens when warm, humid air touches the surface of a cold glass of beer. In the dryer, the liquid water is collected by a moisture separator and discharged out of the system via a drain valve. Sizing a compressed air dryer is not as simple as matching the published CFM rating of the dryer to the flow of the upstream compressor supply. System pressure, inlet compressed air temperature, and room temperature are factors that significantly affect dryer performance and complicate the dryer sizing process. If the dryer is water-cooled, water quality, flow, and temperature are additional factors to be considered. In most compressed air systems, CFM load, pressure, and temperature are dynamic variables. To ensure that the dryer will deliver dry air 100% of the time, it is critical to size the dryer for the worst-case combination of these variables. The worst-case conditions put the greatest heat load upon the dryer, and the refrigeration system must be able to handle this maximum heat load. These worst-case conditions include maximum SCFM, minimum pressure, and maximum temperature of the inlet and ambient air. Where does this worst-case data come from? The best source is to have a trained compressed air specialist to perform a system assessment on your system. The system assessment provides accurate flow and pressure data. Temperature measurements of the inlet, discharge, and ambient air will allow the specialists to calculate dryer inlet temperature extremes based on seasonal compressor room ambient temperatures. Let's look at a real-life example to see how flow, pressure, and temperature affect dryer sizing in a system with the following equipment and having a pressure dew point target of 38 degrees Fahrenheit. The supply is 100 horsepower variable frequency drive lubricated rotary screw compressor, delivering 150 CFM to 450 CFM at 100 psig. The target pressure of the VFD compressor is 100 psig, measured at the discharge of the compressor. Before entering the dryer, the compressed air passes through a general-purpose 500 CFM coalescing filter that has a pressure drop of 4 psig. The air is then treated by the refrigerated air dryer that will deliver 38 degrees Fahrenheit dew point air to the dryer receiver. For this example, the results of the compressed air system assessment show that there are times when the compressor is delivering its full capacity, but the system demand is greater than the compressor supply, and the system goes into drawdown with dryer inlet pressure dropping to 85 psig. In the afternoon, the compressor room heats up to 105 degrees Fahrenheit, and the temperature of the air entering the dryer reaches 110 degrees Fahrenheit. Based on this data, the worst-case conditions for which the dryer must be sized are 450 CFM, 85 psig, 110 degrees Fahrenheit inlet air temperature, and 105 degrees Fahrenheit ambient air temperature. Most refrigerated dryer manufacturers market their dryers with a nominal SCFM rating at a specific dew point temperature under specific industry standard conditions. In the United States, these industry standard conditions are 100 psig inlet pressure to the dryer, 100 degrees Fahrenheit inlet air temperature at the dryer, and 100 degrees Fahrenheit ambient air temperature surrounding the dryer. If any of the three conditions are different from 100, 100, 100, then correction factors must be applied to the nominal rating of the dryer to obtain the actual rated flow of the dryer at the actual conditions. Dryer manufacturers publish correction factors to be used when the equipment is operated under conditions different from the standard 100, 100, 100 conditions, as demonstrated in our example. These factors can either be divisors or multipliers, depending on the specific dryer manufacturer. In this instance, we are using the factors as divisors. In our example, the worst-case conditions are different from the 100, 100, 100 dryer sizing standards, as highlighted in yellow. The measured maximum flow into the dryer must be corrected according to the following formula. Corrected flow, CFM, equals maximum measured flow, which in our example is 450 CFM, divided by pressure factor 0.93, divided by inlet temperature factor 0.8, divided by ambient temperature factor 0.93. The corrected flow of 650 CFM represents the maximum heat load that the dryer will be required to handle. The final step is to choose a dryer from your preferred manufacturer. In our example, a dryer with a rated capacity of at least 650 CFM will always provide a constant 38 degrees Fahrenheit pressure dew point and keep the compressed air system entirely free from liquid water provided the following three conditions are met. 1. The dryer is well maintained, with its condenser fins kept free of blinding dirt and lint. 2. Compressed air is not exposed to a temperature lower than 38 degrees Fahrenheit. And 3. The system incorporates a suitably sized water separator and dependable drain after the dryer discharge. When these critical components are not installed or they malfunction, the system becomes flooded with the liquid water that the dryer effectively condenses from the compressed air. Once contaminated with liquid water, the entire system must undergo an extensive dry-out period following the correction of the contamination problem. When this occurs, it is common for the frustrated maintenance supervisor to replace the refrigerated air dryer with a desiccant dryer that can deliver a minus 40 degrees Fahrenheit pressure dew point. The desiccant dryer solution is overkill and can be avoided if the refrigerated air dryer is properly sized based on actual system data and installed according to best practices. In addition, unless the desiccant dryer is properly sized and installed, it too can create a water problem in this system. An undersized refrigerated dryer, or a dryer that lacks functioning water separators and drains, will eventually allow the system to become contaminated with liquid water. Proper sizing and installation of refrigerated dryers and compressed air systems will ensure a dependable, efficient, and consistently dry supply of compressed air for many years. CAGI sponsors a performance verification program for refrigerated air dryers that provides a uniform and commercially practical media of verifying participants, published flow, and outlet pressure dew point ratings. Visit the CAGI website for more information on this program and for a list of participants.